Hello, everyone. I'm Adrian, working as an ML scientist at Freenome. Today, I'm excited to present here on the opportunities of NLP in cancer screening. I will first discuss some background and then dive deep into a case study on how we applied BERT-based fine-tuning and the LMM fusion learning to perform cancer status classification and end with some discussion and conclusion. I hope you can get to know about cancer screening and the exciting opportunities of NLP could pull here from my presentation. Firstly, what is cancer screening? Cancer screening aims to detect cancer and precancerous conditions at asymptomatic stage. They are important for healthcare as cancers detected at the early stage are much more treatable and has much better health outcome. For example, colon cancer detected at localized stage has about 90% survival rate as compared to 14% when found in metastatic stage. So to decrease cancer-related death, Affordable Care Act has required insurance to cover cancer screening costs for cancers with A or B rating under the USPSTF guidelines. And those cancers include breast, cervical, colon, and lung cancer for 30 patients. However, even patients don't have to pay any out-of-pocket. Cancer screening rates are still low. Study found only 59% of eligible patients are up to date with their CRC screening test. So how to address the problem? One of the effort to address this problem is to provide convenient, non-invasive, and at the same time high accurate blood-based cancer screening tests. Study found that 2 out of 3 patients would prefer a blood-based screening option, and a 70.5% increase in the screening rate could be achieved when blood-based test is added as option. So Freenome is one of the leading companies in this hot space where we're developing our multi-omics platform for cancer screening. The platform will process blood samples and then use our multi-omics platform to measure the biomarkers and then use the machine learning classifier to identify cancer and precancerous patients. The first application of this multi-omics platform will be used for CRC screening, and the performance will be evaluated through the preempt CRC clinical trial. So how do NLP play a role in cancer screening? Next, I will talk about a case study which we published in NLP industry last year on how NLP can assist this effort. This paper is titled Improving Precancerous Case Characterization via a Transformer-based Ensemble Learning. This is a collaborative work with other amazing team members at Freenome. So why do we care about precancerous stage? So for CRC, it progressed from healthy to precancerous stage that include non-advanced adenoma and NA and advanced adenoma A, and then to carcinoma. The preventive screening test aim to find patients at A and CRC stage. In order to develop our test, we have recruited tens of thousands of patients in the discovery studies and preempt clinical trial. We have measured their blood biomarkers and offered free colonoscopy to these patients in order to determine their cancer status. Colonoscopy has been the gold standard to diagnose colon cancer. During colonoscopy, suspicious polyp will be removed and examined in the pathology lab. And the resulting colonoscopy and pathology reports clearly document the size and pathology type of each collected polyp. And the classification of the patients into CRCA, NA, and negative are based on the information from the free text sections in the reports. And the classification system can be pretty complex, especially for the precancerous stage A and NA. For example, the A cases include these 5 different scenarios. If any size of the villous growth pattern polyp is considered A, but for a regular adenoma, it has to be larger than 1 centimeter in size. You may want to ask, can we use a structured code such as ICD or CPT to extract this information? Unfortunately, the current existing codes are not granular enough to encode such detailed information. For example, the closest SCD or CPT codes only mention any detected polyp, but not the size or the type. So right now, we solely rely on the pathologist to manually review these documents, and this can be pretty cumbersome for the large number of involved participants. Therefore, we are interested in using NLP methods to automatically classify patients to replace this manual process. NLP has been applied to process colonoscopy and pathology reports in the earlier work with some limitations. Firstly, most NLP applications focus on extracting cancer cases and largely ignore the precancerous cases. This may be due to the focus to assist the cancer registry collection, but for cancer screening, we are particularly interested in the precancerous cases. But it's more challenging to extract precancerous cases because the terminology is much more variable and less standardized. Secondly, previous application to colon cancer focus on extracting individual attributes, such as the adenoma size, but they did not have an end-to-end algorithm to classify patients into these different categories. And that is especially important to creating the ground truth label for cancer screening test development and to identify high-risk patients. Thirdly, a lot of NLP applications in the biomedical field still heavily rely on the rule-based system, and they did not take advantage of the advances in large pre-trained language models. So here in our study, we developed a highly accurate transformer-based ensemble learning method for end-to-end precancerous case and attribute extraction. The data we used in our study include health records for over 3,000 patients collected from 68 collection sites across the US. The data has been annotated with patient-level cancer status, and a subset of around 800 documents have token-level annotation for the lesion size. For the experiment, we first digitized the document with OCR and then extracted text for the sections that are only relevant to the cancer diagnosis from the reports. And we formulate this cancer status extraction as a classification task and evaluate the performance of bag-of words, CN, and fine-tuning of Bell-Bird model. All models achieve over 0.8 macro F1 score and has high accuracy for negative and CRC, which both over 0.9 F1 score. But we found Bell-Bird model outperformed the bag-of words and CN for the precancerous cases and A and NA. This suggests that the uniform features or short phrases are sensitive to classifying cancer or healthy, but the Bell-Bird's ability to capture long-range interaction help increase the sensitivity to differentiate the precancerous cases. To identify the source of incorrect prediction, we performed the error analysis based on the Bell-Bird's classification result. We found the misclassification are usually confusions between A and NA. For example, 68% of the incorrect prediction for NA are wrongly classified as AA, and the 65% of the incorrect prediction for AA are wrongly classified as NA. Therefore, it's critical to improve the separation between A and NA. So how to do that? With the help with the domain knowledge, we found lesion size is an important factor to distinguish these two classes. Therefore, we propose to explicitly add lesion size as an additional feature to improve the performance. So for the lesion size extraction, we formulated as a named entity recognition task. We first evaluated directly fine-tune the BERT model on our small number of documents with token level annotation. And unfortunately, this model has low precision and recall score and also the F1. We next asked, are there any existing pre-trained models that we can use for transfer learning? We didn't find any public available model pre-trained or fine-tuning for the biomedical corpus, but there is a model pre-trained with the ontonode corpus to extract quantities or measurements for weight and distance. So we directly apply this model to evaluate its ability to extract lesion size. Interestingly, this model increased the recall score but still have low precision. So finally, we continue fine-tune this pre-trained onto-node model on our lesion size data set, and this helped to achieve large improvement in both the precision and F1, precision and recall, and also the F1 score. And this suggests that transfer learning from even a non-biomedical domain can still help with the domain-specific NLP test due to the high task similarity. So next, we combine the extracted lesion size and BERT classification probabilities as an ensemble model through a shallow random forest layer. And this model indeed helped to improve performance for the A and the NA classes compared to the fine-tuned BERT model alone. And the overall F1's micro F1 score increases from 0.914 to 0.923. This suggests that this ensemble model with domain knowledge-informed feature engineering can improve upon direct fine-tuning. This work was published last year. However, we have seen a transformative change in the NLP space based on LLM and generative AI. So, but our data and results serve as a great benchmark to evaluate the LLM's potential to do few-shot learning for this complex phenotyping task. And recently, a lot of open source tools have made evaluating LLM for HIPAA-protected biomedical data on limited computational resource possible. Firstly, there are open source models available, such as Llama, to enable in-house inference on privacy-sensitive biomedical data. And secondly, tools such as Accelerate help to handle the distribution of billions of model parameters to multiple GPUs and handles the weight transfer from CPU to GPU. And finally, tools like Bits and Bytes performs 4-bit or 8-bit model quantization to further reduce the memory requirement to do inference on billion number of parameters large language model. So we did some preliminary assessment. We randomly selected 400 samples and used Llama 2 with different parameter space and experimented with techniques with different prompting, with basic prompting and different techniques such as in-context learning and chain of thoughts for the few-shot learning ability. And for the computational resource, we used 4 A100 GPU and with each 40 gigabyte memory. Here shows the performance for the LLM few-shot learning. Here shows the performance based on the LLM few-shot learning. We found the performance generally increased with the parameter space, and we tested different prompting techniques based on the 13 billion model and found chain of thoughts provide dissonant boost in the model performance. However, few-shot learning based on the 70 billion model still has much lower performance than the BERT-based fine-tuning. Some other challenges we encountered here include additional efforts needed to process the model output for the classification task, especially for the small model. And we found around 10% of the samples cannot fit the context window. So even though LLM-based few-shot learning sounds attractive, fine-tuning for LLM is still needed for this complex phenotyping task. To summarize, our study had some limitations. First, we didn't fully evaluate how OCR of these scanned medical reports could affect performance. Firstly, it's challenging to extract the relevant sections from the reports. As in the electronic report, we can leverage the format, but for the scanned documents, we have to use a heuristic approach to identify the relevant bounding box. And secondly, we observe some errors in the OCR that could affect performance negatively. Second limitations, even though this data set used in the study is collected from 68 collection sites across the US, the data may not fully capture the variability in the real-world data. It will be interesting to continue monitor the model performance with the real-world data after deployment. Lastly, we didn't evaluate how many samples are needed to fine-tune the BERT or LLM model. Maybe the LLM requires much less samples to fine-tune than BERT, but that need to be evaluated against the cost from the huge computation and the storage burden for fine-tuning LLM. In conclusion, we found NLP is especially useful to support cancer screening, as cancer screening focuses on precancerous conditions, which are mostly documented in the unstructured sections of the EHR. And our best model achieved a 0.924 macro F1 score for an algorithm that can perform end-to-end cancer and precancerous case characterization that is important for the development of a cancer screening test. And we found fine-tuning of the transformer model are inadequate for the domain-specific task, and a good understanding of the data, the problem, and the combination with different techniques such as feature engineering, transfer learning, and ensemble learning is important to improve performance for real-world problem. This framework can be used to extract other disease phenotyping, and this will help to unlock the huge information power of the electronic records to improve patient care and health outcome. And lastly, we evaluate the open source models and found based on the few-shot learning-based performance still underperformed the BERT-based fine-tuning. Thanks so much for your attention, and feel free to reach out for further discussion.
This concludes today's sessions. I'd like to extend my appreciation to the speakers for their comprehensive discussions on NLP's role in healthcare and life science. We've seen firsthand the potential and the challenges from improving healthcare record analysis to aiding in early cancer detection and refining treatment plans. We continue tomorrow at noon for the third day of the NLP Summit, diving into AI applications in sectors like finance, retail, manufacturing, and advertising. See you tomorrow. Enjoy the rest of your day.